Hello everyone. In this video, I'm going to go over a few of the practice test questions with you and how to do them. So the numbering on these might be off from what is on your practice test, in which case, sorry about that. So let's look at number 2 from the non-proof questions. Consider the set U, which consists of all complex numbers a plus bi, such that a squared plus b squared equals 2. So if you're familiar with complex numbers, this is like the square of the modulus. If you're not, it's just kind of a standard thing to calculate for complex numbers. It's the real part squared plus the coefficient of the imaginary part squared. So this set consists of all of those where a squared plus b squared equals 2. And then just specifying here, of course, I is the square root of -1, the imaginary number. And then we're doing the usual addition and multiplication operations. Give a counterexample showing that U does not satisfy ring axiom 1. So ring axiom 1 is closed under addition. So all we have to do is find two complex numbers that are in the set U, where when you add them, the result is not in the set U. Okay? So if you look at let's look at the little cheat sheet here and the list of ring axioms just to point out like why this is what you have to do. Let's see. Gosh, where are they? Oh, here we go. Okay, so closure for addition. So basically you want to prove the negation of this. So the negation is going to be there exist A and B in the ring such that A plus B is not in the ring. So if you need to review your negations for these, remember you flip all of the quantifiers, and then for the inside statement after the quantifiers, you negate that. Okay, so the negation would be there exist A and B in the ring, or the set, such that A plus B is not in that set. So that is why we're looking for, in this problem up here, we are looking for two elements. I'm not going to call them A and B here because that would be a little bit confusing. We've already used A and B in this setup. Let's say we're looking for X and Y such that X plus Y is not in U. Okay, so that is the strategy here. So I'll just, why is my tab not working? Okay, so strategy, you don't need to include this part on your actual test, but like the strategy is find X and Y in U such that X plus Y is not in U. And you want to kind of go as easy as possible. So actually, I think I went too hard on the other solutions, the written solutions. I can do this way easier if I just take them to both be like real numbers, because real numbers are a subset of the complex. So a real number A without the imaginary part that would satisfy this equation right here would be like square root of 2. So let's say, let's let X be just square root of 2. Okay, and then let's do, again, let's just make it really easy on ourselves and just use it again for Y as well. Okay, so then X and Y, then we have that the real part squared is, just in case it wasn't like obvious that X and Y are in the U set, they're in there because when you calculate the A squared plus B squared thing for both of them, you get this, okay, which satisfies the equation for membership in U. All right, so X equals Y are in U. However, if we add them together, X plus Y is going to be 2 times square root of 2. And if we do the A squared plus B squared thing to that, then we have 2 times square root of 2 squared plus 0 squared. That is going to be, let's see, 4 times 2, 8. That is not equal to 2. So X plus Y is not in U. Okay, so that is a counterexample. We have found X and Y in U, where X plus Y is not in U. Okay, I think pretty much almost every set you could think of, like a subset of the complex numbers, it would rarely have It would rarely be closed under addition. You'd have to think of something really special for it to be closed under addition. Okay, I'll worry about formatting that later. All right, next question. Okay, so part B here. Give a counterexample showing that U does not satisfy ring axiom 12. So ring axiom 12, you can just look at it if you forgot what it was. Here they are. Okay, so we're going to be trying to show the negation of this one. So it is going to become, there exists an element in the ring, a non-zero element. So this quantifier part stays the same, except that the quantifier flips. So you're not going to negate this part right here. It's just going to flip to there exists an element with this property. So there exists an element, we can call it A in R, or U for us, where A is non-zero, such that for all, so that's going to flip, such that for all B in, for us it's going to be U, and then such that is the words that go with there exists. So when this becomes for all, it's going to be for all B in U, AB is not equal to 1. Okay, so for negation here, let's just type out like, negation of 12 is going to be, oops, there exists A in R, and I put in such that because that just goes with there exists. Oh, I forgot the where part. That stays the same. Specifications on the type of element stay the same. Where A is non-zero, such that, and then the exists one flips to for all, B in R, comma, and then we negate this inside statement, AB does not equal 1. Okay, so if you read this carefully, you can understand what this is saying is there's some element in the ring, a non-zero element in the ring, such that none of the other elements are its multiplicative inverse. Okay, so it's saying for every other element, it's not the inverse of A. So basically, there's a non-invertible element in the ring. That is what you're looking for. So let me go put the spec up here with the problem. Okay, so you have to know what you're looking for in order to do these problems. Okay, so now how do you find a non-invertible complex number? So if you've taken complex analysis or you are taking it, like you have some advantage here because you would know that the modulus or the size of the inverse is basically like inverted. So if we have a complex number where a squared plus b squared equals 2, then its inverse would have a squared plus b squared equals 1/2. But if you don't know that, you can just kind of try some like random element. And actually, there are not any invertible elements in U, so no matter what you try, you'll find that it's not invertible. Okay, so let's just try like, you know what? I think, again, I even made it too hard on the other solutions. Like, I could have just picked a real number. A real number would have also worked. Okay, so let's just say I'm going to use x and y here again instead of, I'm going to change these to x's and y's because we already had a and b in the problem statement. Okay, so change those to x's and y's. Okay, so let x be, I guess the only one that's a real number that would actually be in this set U would be either plus or minus square root of 2. So I'm just going to use x is square root of 2 again. Okay. And the multiplication operation here is the regular multiplication. It's the same one for real numbers. It also works for complex numbers. So the multiplicative inverse of x would be 1 over square root of 2. Okay. So we don't even really have to solve for it if we're just doing regular real numbers. Multiplicative inverse of x, oops, x would, okay, my daily struggle with word, would be 1 over x, which is 1 over square root of 2. But what we're going to then show is that when you have that and you submit it to this membership test here, a squared plus b squared equals 2, it is not going to pass the test. Because if I square that part and then the imaginary coefficient is 0, I'm getting 1/2, which is not 2. So 1 over x is not in u. Okay. So that's actually an easier solution than the one I had on the other solutions, but either way works. Actually, like I said, any element that you would pick for x, you would actually find that its inverse is not in u. And if you don't know the procedure for finding the multiplicative inverse of a complex number, there is a particular way to do it, but you could also just solve for it the way I had shown in the other solutions. Okay, let's look at number 3 now. So consider the set R. Let me just make sure I'm still recording here. I get a little bit paranoid. Yes, okay. Okay. So consider the set R real numbers with the operations plus and star. So plus is normal addition, and star is this wacky multiplication operation given by this formula here. This is the formula if you've ever taken physics for like adding the capacitance of capacitors in a connected in series or resistors connected in parallel. Anyway, so give our counterexample showing this does not satisfy ring axiom 6 and a counterexample showing this does not satisfy ring axiom 8. So again, I would just go to those axioms, look up what they are, and just negate them, and then try to show the negation. So I'm just going to copy these and write out their negations. Okay. So that's that one. And then, okay, so the negation is going to be, so instead of for all, it'll be there exists, A, B, in this case, our set is going to be real numbers. So I'll just go ahead and put that in. Such that, and now instead of the regular multiplication here, again, I'm going to use the symbols for the one that we were given. So A star B is not in reals. Okay, so that's for part A. And then for part B, put that in there as well. So I have to get everything formatted the way I like it. Okay, so then the negation for this one is going to be negation is going to be there exists A, B, C in reals. And then since it became exists, I'm going to use the word such that. And now this inside statement here, we're going to negate this. So be a little bit careful because it is an and statement. So the negation is going to be an or. It's not necessary that both of these be false, just at least one of them. Okay, so this is going to be A times B plus C not equal AB plus AC or A plus B times C does not equal AC plus BC. Oh, but I already did something wrong here, right? Because it's not regular multiplication. It's that weird star operation. So I'm going to write it with the star, just so I don't get it twisted and think I'm calculating something different, like regular multiplication. Okay, so that is what I'm going to try to prove. I can never get these indentations quite. Okay, so let's look at part A here first. So I'm trying to find real numbers A and B such that A star B is not a real number. And if I look at the formula here, I'm just trying to think of any real A and B that I could plug in that would have a non-real result. And the only thing that can go wrong with division in the real numbers is if you divide by 0. And 0 is not excluded from the set, so indeed I could plug in 0. Okay, so I'm going to let I'm just going to use 0 for both of them just to make it easy. Okay, so then 0 star 0 is 1 over 0 plus 1 over 0, which does not exist as a real number. Okay, so that is our counterexample right there. For part A, it's pretty easy. For part B, it's going to be a little bit trickier. I need to find A, B, and C in the reals such that one of these equations doesn't hold. I don't really have a good idea of like what kind of numbers I should be looking for, so I'm just going to try some random numbers and I'll just kind of hope they work. So easiest numbers to work with would be like ones and zeros. Why can I not tab in? Okay, there we go. All right, so I'm going to let, I think in the other solutions I just used 1, 1, and 1. I could maybe try using like, I don't know, if I did like 1 and 0, we could do like 1, 1 and 0. Well, actually, I already know putting 0 into the multiplication like doesn't work at all. So I guess I'd already get a non-equals on one side. So let me try doing that. So we'll do A and B, make those 1, and C equals 0, maybe. Okay, then I'm going to try calculating both sides of this one and see what they come out to be separately. See if they're non-equal. Okay, so the first one should be 1 star 1 plus 0. The plus is just regular, so this is just 1 star 1. And then, oops, I somehow cut off the end of, this should be star C, right? Okay, so this is going to be 1 star 1, which is okay. And then I'm going to have 1 star 0, and I already know 1 star 0 is not going to exist. So this is going to be D&E, not a real number. I guess if you really want to like see why, you can try plugging in 1 star 0 and you get 1 over 1 plus 1 over 0. Oops, not P0. Which does not exist or is not in the real numbers, you could say. All right, and then this one right here, that's going to be 1 over 1 plus 1 over 1, which is 1/2. So 1/2 is not equal to whatever this non-real thing down here is. Okay, so the equation is not satisfied. All right, so we found what we were looking for, A, B, and C in the reals, such that this first equation here was not true. All right, so now let's get into some more polynomial type of ones. So give a counterexample, I think this is number 5, to show the following statement is false. For any ring R and any polynomials f and g in R bracket x, the degree of f plus g is equal to the max of the degree of f and the degree of g, and make sure to specify what ring you're using. So again, I would just start off by making sure you understand the negation of the statement. And you don't need to put this in your write-up, but you have to at least know what it is in order to be able to get the counterexample. So negation of the statement is, we're going to turn this for any into there exist. Okay, so that's not how you spell exists. Exists. There exists a ring R and polynomials in the polynomial ring made from that. So f of x, g of x, in, having a little trouble typing today, r of x. And since we are using there exists, we need the word such that here for the English grammar. Such that deg, I'm just going to abbreviate this as f plus g, does not equal, so we're negating the inside statement here, max deg f deg g. Okay, so I'm just doing a little bit of abbreviation with leaving out the x's there. Okay, so I'm looking for a ring, and I'm looking for 2 polynomials in the polynomial ring made from that ring, such that the degree that I get for when I add the 2 polynomials together is not the same as the max of their 2 degrees. So if you don't really have any idea what to do, you could just try some stuff. Just try some like random rings. Maybe everybody likes real numbers the best, right? So I don't know, just make up some random polynomials. I don't know, 2x squared plus x plus 1. G could be, I don't know, 3x plus 5 or something. Just some random numbers here. Then for f of x plus g of x, we would get 2x squared plus 4x plus 6. So does that satisfy the equation or does it not satisfy? So the degree, so let me check on the degree of them all separately. So f would have degree f equals 2 here, and then g would have degree g would be 1, and then the degree of f plus g would be 2. And then if we compare that to the max of degree f and degree g, so max of degree f and degree g, we can calculate right here. Max of 2 and 1 is 2. Okay, so we do see that the equation is true for this random example that I made up. I'm looking for a situation where that equation is not true. So, what can I do? Maybe I need to somehow, I don't know, make these the same degree, maybe? I could try something like that. So instead of having 2x squared here, that would be 5x squared. Then here I'd just have x. Okay, well, that changed this number to 2, but the equation here is still true. So I think what I need to do is make these two leading terms here cancel out. So if I make this one negative 2x, then down here I'm going to drop the degree on their sum. Okay, so I'll just have x plus 6, and that has a degree of 1, which is not the same as the max of the degrees of the two original polynomials. Okay, so you can just start off with like an example that doesn't work and then just kind of fidget with it or tweak it a little bit when you see what's wrong with it until you get what you're looking for. Alrighty, let's look at number 8. So give a counterexample showing the following statement is false. For any field f and any f and g in f bracket x, f and g induce the same function from f to f, if and only if they're equal as polynomials. Right, so this is something that you always thought was true probably until this class. You never distinguished between what the function is and what the formula is. You always were thinking that they were like one and the same thing, basically. You could get one from the other. But for the first time in this class, we saw some fields where that is not true. That's because we looked at the Zn and the Zp rings in this class. So your counterexample has to come from those. You cannot use an infinite field. We had actually shown, I think it was the day where I did the video notes, that in an infinite field, two functions being the same, or the induced functions being the same, means that the polynomials have to be the same. So this will only work for finite fields. All right, so we must use a finite field, but let me go ahead and write the negation out here. So again, I'm switching these for any's to there exists. All right, so there exists, oops, field f, and some, no, I'm not trying to type a different language, Microsoft, and some polynomials f of x and g of x in f bracket x, such that, okay, now I need to negate the inside statement here. So whenever you have a statement like this, you need to kind of look at what is the outermost logical connective here. I guess when I thought it was only this statement here, I was going to say to negate the verb here, but then I noticed there's an if and only if right here. So when you're negating an if and only if statement, if and only if asserts that the two parts have the same truth value. So if you want to show that it's that an if and only if is not true, you need to find a situation in which the two parts have opposite truth values. So you have two ways to do that. You can either find a situation where this left half is true and the right half is false, or you could find a situation where the left half is false and the right half is true. But now think about that second one for a minute. If the right half here is true, the formulas are the same, the induced function will definitely be the same. If the formulas are the same, then no matter what field you're in, the induced function will be the same. Okay, so your only real choice here is to find one where they do induce the same function, so left half is true, but right half is false. Okay, so I'm going to kind of summarize here such that the left-hand side and right-hand side of the IFF statement have opposite truth values, which can only happen when left-hand side is true and right-hand side is false. So we're looking for f of x, well, rather for the field, oops, f of x, g of x, such that, so we want f and g induce the same function. Oops, I'll just abbreviate by saying fg induce same function, but they are not the same as polynomials. So in other words, they have different formulas. Okay, so that's all kind of background information. You don't need to include this on your test paper, but that is what we need to look for. Okay, so the only way this can happen to have two different formulas inducing the same function is actually if you are in a finite field. So let's do this in a finite field, and I'm just going to make stuff real easy on us. The finite fields, remember, a field has no zero divisors, so these are the z sub n's where that n is prime. Okay, and let's just use the easiest one. It's z2. It's only two elements, so let's use z2, which is a field. So we're going to use that one because it's easy. And let's try to think of two polynomials that have different formulas, but they induce the same function. So how do you know if they induce the same function? Well, you just have to make sure they map the elements to the same places. So we just need to come up with, they need to both send, wherever f sends 0, g needs to send it to the same place. And there's only two things to, what am I doing? There's only two things to check here. Okay. Where does f send 0? Where does g send 0? Where does f send 1? And where does g send 1? Oh gosh, I can't type and talk at the same time. Sorry. You guys someday try typing and talking at the same time. Okay. So can we just make up a function that sends everything to 0 maybe? Would that be like the easiest thing? So for one of them, I could just use the formula 0, right? And then for the other one, I just need to come up with like another formula that sends everything to 0 that's not 0. So how about like I just put in the two factors, like x minus the first root, x minus the second root. So like x minus 0, x minus 1. So just x times x minus 1 basically, right? Won't this do it? I think this will do it. Okay. Okay. Let me just make sure I'm recording. Okay, yes. All right, so number 9, the last one from non-proofs that I wanted to go over, factor into irreducible monic polynomials. Yeah, so I want to make sure that you guys did actually learn how to do this. So you're going to go into irreducible polynomials, make sure that they're monic, and then if they're all monic, you should need just like one single constant possibly as another factor. So we could go ahead and like factor out the 4 at the beginning, or we could do that at the end. I think I did it at the end in the other solutions, so maybe I'll do it at the beginning for this one. So how do we factor out the 4? So what you gotta ask yourself is, let me go ahead and put this in blue. Okay, so factor out the 4. So I'm gonna do f of x equals, f of x equals 4 times what? So first I have x to the 4th. Now I cannot do 5 over 4 because I'm in Z7, so I'm not allowed fractions. What I have to ask myself is there something that is congruent to 5 that I can pull a 4 out of? Okay, so things that are congruent to 5 mod 7 are like 5 minus 7, which would be negative 2, 5 plus 7. So 5 plus 7 is 12. Okay, so that I can pull a 4 out of, right? And it will become 3. Okay, and then the same thing for here. What is congruent to 2 that I could pull a 4 out of? So if I do 2 plus 7, that's 9. If I do plus another 7, I get 16. And I can pull a 4 out of that. Okay, and then same here. So -1 is congruent to 6. If I add another 7, let's see, that's 13. Add another 7, that's 20. Okay, so 20 is good, and I can pull then the 4 out, and I'll be left with 5. And then pulling a 4 out of 1. So if I add 7 to 1, I get 8. I can pull a 4 out of that, which leaves me with 2. Okay, so at this point, you would just want to confirm that when you multiply this back out, you do get all the numbers you started with. Okay, so I would get 12x cubed, 16x squared, 20x plus 8. And let me just confirm those all reduced to what they were before. Okay, so I had 4x cubed, yep. 12 mod 7 reduces to 5. 16 mod 7 does reduce to 2. Let's see, 20 mod 7 reduces to 6, which is the same as -x. And then 8 mod 7 is 1. Okay, so this is good. I can do this. Let me actually I should reverse the order of what I did here. So it looks like I was going this way. And it must look better for someone who's like reading it over by themselves later. Yeah, so I started with that. I replaced everything with coefficients with things they were congruent to that had factors of 4, and then I factored the 4 out. Okay, cool. So now what I want to do is factor this part that's left over, which, as you can see, it is now monic. So to figure out what the factors are, I want to check for linear factors first, and I can do that by checking for roots. So I'm going to check for roots of this part by plugging in 0, 1, 2, 3, 4, 5, and 6, which are the only elements in Z6. So by plugging in elements of, or Z7, did I say Z6? Okay. So when x equals 0, I get 2. When x equals 1, I get, let's see, so 1 plus 3, so that's 4, plus 4 is 8, plus 5 is 13, 14, 15. I get 15, which is congruent to 1. Okay, x equals 2. This becomes a little bit tedious at some point. Okay, so I get 2 to the 4th, 16, plus 3 times 8, 24, plus 4 times, that's going to be 4, another 16. 5 times 2 is 10, plus 2, hold on. I think that is 68, which modulo 7, let's see, 63 is a multiple of 7, so that's 5, I think, hopefully. I guess you guys can bring a calculator if you want. When x is 3, okay, we get 3 to the 4th, that's 81, plus 3 times, oh, that's 3 to the 4th again, so another 81. All right, 4 times 9, that is 36, 15, plus 2, blah. We can reduce these individually, mod 7 as well. You don't have to do it, like, you don't have to add them all together and then reduce mod 7. So let's see, 77 is a multiple of 7, so 81 mod 7 should be 4. The other 81 also gives us 4. 36 mod 7 is 1. 15 mod 7 is 1. And then there's 2. Oh yeah, that's easier like that. Okay, so I get 8 plus 2, 10, 12, which is 5. Okay, now for the others, for instead of doing 4, you can do -3 if you want, because 4 is congruent. Sorry, if you're doing x equals 4, that is the same as -3. I just think that's a little bit easier because then things stay as small numbers for when you're taking the powers. So -3 to the 4th is 81 again. And then we have 3 times -3 to the 3rd. So that's going to be -81. So you see things are already canceling out. And this is going to be 4 times 9, 36. And then minus 15. and then plus 2. Okay, so 36 minus 15, 21 plus 2, 23. Mod 7 is 2. Okay, then for x equals 5, that is the same as -2, which is easier to plug in. Okay, so I'm doing -2 to the 4th, 16 plus 3 times -8, so that's minus 24, plus 4 times 4 is another 16, minus 10, plus 2, how does this simplify? Okay, 32 minus 24 is 8, minus 10, -2, oh, I think I got a 0 here. Okay, and then the last one, when I plug in 6, that is the same as -1. Much easier to plug in. So -1 to the 4 is 1. Let's see, minus 3 plus 4 minus 5 plus 2. Okay, what does this come out to? Let's see, boop, 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 -1. All right, so it looks like the only root was at x equals 5. Gosh, I hope this is the same as what I got from the other problem, or the other solution that I did. So only linear factor is our going to be x minus 5, or if you want, since x minus 5 is the same as plus 2, you could also write it like this. That might actually make it easier to divide out. But we don't actually know how many factors of this there are. So there could be 1 factor of it, there could be 2 factors of it, there could be 4 factors of it. So once you divide it out once, you have to try dividing it out again until it's not a root anymore. Okay, so we'll try dividing this out of this thingy up here. Okay. All right, so I'm going to try, it looks atrocious when I try to do this by hand on my computer, so I'm going to try doing it with a table, and we can try to kind of, I don't know, this is not going to look great no matter what I do, but let me try doing it like this. So put up borders here, here, here for like subtractions. Okay. All right, let's try doing this and see what happens. Okay, I just paused it and like reformatted this until it wasn't driving me crazy. Okay, so we're gonna try dividing x plus 2. Oh, no, come back. X plus 2 out of this polynomial. And I'm going to do it with a table because my handwriting is not good. Okay, so first we want to ask ourselves, what can we multiply x by to get x to the 4th? And that would be x cubed. So we're going to put x cubed up here. Then we multiply x cubed times this whole part here. And we're going to subtract whatever we get. Okay, so we're going to subtract x cubed times x plus 2. So that'll be x to the 4th plus 2x cubed. Oh yeah, I like using x plus 2 instead of x minus 5. I think this is already simpler. Okay, so x to the 4th and x to the 4th cancel out. And then we're doing 3x cubed minus 2x cubed. So that is going to be x cubed. And then we have to just bring all of these ones down. So I'm just going to copy them, put them down here. Okay, so now we're dividing this by x plus 2. So we ask ourselves, what do we multiply x by to get x cubed? It's obviously just x squared. So we're going to put x squared up here. Then we're going to multiply that x squared by x plus 2. And we'll subtract whatever we get. So x squared times x plus 2 is x cubed plus 2x squared. And we're subtracting that from this line. So we're going to be left with 2x squared, and then this extra terms are going to come down. Okay, and then what are we multiplying by x to get 2x squared? That is going to be 2x. So we're doing 2x times x plus 2, and we're going to subtract the result. So that's going to be 2x squared plus 4x. Okay, and when we subtract that, we're going to get 5x minus 4x is going to be just x. And then we're going to have left over. Oh, we have x plus 2 left over. Oh, perfect. Okay, so then for the very last one, it's going to go in exactly. We're going to put 1 up here, and we're going to subtract x plus 2, and we're going to have a remainder of 0, which is great. And we should have a remainder of 0 because we already knew that x plus 2 had to be a factor of this original polynomial right here. Okay, so what we just found out is starting from the very beginning, f of x was equal to 4 times this, and we just divided out x plus 2 from that. So this is 4 times x plus 2, which x plus 2 is also monic, and we're left over with this right here. Now, we don't need to check for all the roots again, because anything that's a root of this polynomial was a root of the original polynomial. We know that only 5 or -2 was a root of that, but it's possible that 5 or -2 could still be a root of this part right here. So we need to check whether x equals 5, which is the same as -2, is still a root of this part by just plugging it in. Okay, so if we plug in, I'm going to do it with -2 because I think that's easier. What do we get? So -2 cubed is -8, plus that's going to be 4, minus 4, plus 1. Uh-oh, I think it is still a root because this is going to be -7, which is the same as 0. Yeah, so we have another factor of x plus 2 in this part here. So we need to divide that out again. Okay, so we're going to do another division. All right, so we're dividing that thingy by x plus 2 again. All right, so what do we need to multiply x plus 2 by to get x cubed? That is going to be x squared. So x squared times x plus 2, we're going to subtract whatever we get. Okay, so this is going to be x cubed plus 2x squared. Right, and we are subtracting, and what do we get? Okay, we're getting -x squared, and then we're bringing down the extra terms, which are 2x and 1. Now, what do I multiply x plus 2 by to get -x squared here? So that's going to be -x. Okay, so I multiply that down here, subtract whatever I get. That's going to be -x squared minus 2x. Okay, and I'm going to get, let's see, -x squared and x squared cancel, 2x, and then it's going to be plus another 2x, so 4x plus 1. And, that looks a little bit weird, like it's not going to go in evenly, but can't really predict because we're in Z7, so I'm just going to keep going and hopefully it works out. So I'm going to need 4 here. And then down here, I'm going to subtract what I get by multiplying 4, so that's going to be 4x plus 8. Oh yeah, that is going to come out evenly. So this is going to be 1 minus 8, which is -7, which is the same as 0. So I do get an even division here. And so what I'm getting here now is that, so just to kind of summarize where we're at, we had this before. Okay. And now we've factored out another factor of x plus 2. So I'm going to put the square on the x plus 2. And then what's left over is now this quotient from up here. So x squared minus x plus 4. Okay. And so what I need to do is we need to check, so I'm trying to format everything just how I like it. We need to check again whether x equals 5 or -2 is still a factor, because we could still potentially have up to 2 more factors of it in this leftover part. So we need to check whether it's still a factor, or whether, not a factor, sorry, whether it's still a root or a 0 of that. Okay, so this time when I plug in x equals -2 to this x squared, minus x plus 4, I'm going to get 4. Okay, so plus 2 plus 4. That is going to be 10, which now thankfully is not 0. Okay, so we got all the factors of x plus 2. And now, does this part here factor x squared minus x plus 4? We know it doesn't factor because nothing else could possibly be a root of it besides the x equals 5 or negative 2, which we just checked. Because we checked all those roots up here at the very beginning, and they were not roots of the entire function. Okay, so that means that this thingy here has no linear factors, and the only type of factor that it could have that would be of lesser degree would be linear. So in conclusion, it does not have any factors of lesser degree, which means it is irreducible. And as you guys can see, it is in a monic form. So our final answer here, we are all done. Why does this tab over too much? So final answer here is this form right here. Okay, and now Microsoft is just messing with me. All right, so that is it for the non-proof questions. And I think what I want to do is continue this in another video because it's getting a little bit long. So I will resume in the next video.